Hello class, welcome to 5.2 Properties of Power Series. We start with combining power series. How can we add or subtract to power series? And for that we will have some definition laid out. And then we look at uniqueness of power series, which is basically if you set two power series equal to each other over the same interval, then those two series must be the same. Okay? And we will work on problems based on that. And then we will also look at how to construct a power series from a known power series. Okay? So combining power series says that if you have two power series, summation Cn x power n and summation Dn x power n 0 to infinity, and these converge to the functions f and g respectively on a common interval I, then these three are possible. The power series, summation Cn x power n plus or minus Dn x power n, adding them together, will converge to f plus or minus g on I. Second is, if for any integer m greater than or equal to 0 and any real number b, the power series summation b x power m Cn x power n converges to b x power m f of x on I. For any integer m greater than or equal to 0 and any real number b, the power series summation Cn b x power m the whole power n converges to f of b x power m for all x such that b x power m is in I. Now every word here is very careful, is to be used carefully because when we look at the problems we will find that we'll have to closely follow this language, particularly the common interval I. Okay. For this I want to take us back to the previous lesson. So let's see that I held it in the right spot. I'll have to scroll it back up. Alright, so this is the part we did last time and I want to kind of focus on that. We said f of x 1 over x is a function that can be represented by the power series when absolute value of x is less than 1. Or in other words, in this interval negative 1 to 1, because absolute value of x less than 1, as I pointed out here in orange, is nothing but negative 1 less than x less than 1. This is what we established last time. And we're going to use this power series representation because you're able to represent a power series as a function. And that is really interesting because once you can write it as a function, then you can do things related to the function, which means you could differentiate, you could integrate and all that, right? So it gives us additional room, additional ability to deal with a power series because of the new representation as a function. So this is something I wanted to call upon. So let's come back here, and if you look at this one, well, the first condition is kind of intuitive, right? If you added the two functions, the two power series together, then they will converge to the sum of their functions on that interval I, because that's the key point there on the common interval I. Look at the next one. For any integer m greater than or equal to 0, well, summation b x power m Cn x power n, that looks really complicated. So let's take a look at that. Okay. So what we are saying is, from the previous lesson, so here's a quick explanation for this. This is something you'll have to really remember, okay? Power series representation is that f of x is equal to 1 over 1 minus x, right? And this was the representation for the power series summation x power n. And if you expanded this, this would expand as 1 plus x squared plus x cubed and so on, right? So this is the key idea here, and this is what we're going to use to deal with this particular section, okay? Now I want you to pay attention to these things. You see this x here, you see that x here, and you see this x, right? So if I change that to, say, x squared, then they will all become x squared. If I change this to something else, then they will all change to whatever that is reflected to be, okay? So as a quick example, to illustrate, let's say, to illustrate the third condition, okay? You see this f of b x power m. So if I were to write this like this, then this whole thing will have to be rewritten as 1 minus bx power m. And that has to be summation n 0 to infinity bx power m. Does that make sense? Because now that you have a new placeholder, wherever you see in the place of x, whatever you see in the place of x, that is what you see represented everywhere wherever x occurs. So that is the idea of f of b x power m. That's because in the place of cn x power n, you now have this information. So let me write that as well. The general series for us is summation cn x power n, right? Or if you had a different, this is centered at 0. If it was centered at a, then you had x minus a power n. And if you recall just now, we saw that this x power n, right? Cn is let's say Cn was some other constant. This x power n is what is represented as f of x. And here, if it's x minus a, that will be f of x minus a, right? And instead of x power n, let's go to the second condition. Oh no, again, third condition. Instead of x power n, you now have b x power m, that power n. So your x power n is replaced by bx power n. That's why you have the function also having not just the regular x, but bx power m. Okay? All right, so this is a general gist of the idea. Let's go ahead and look at uniqueness theorem property, and then we'll look at some problems. Okay? The uniqueness of power series says, if you had summation cn x minus a power n and summation dn x minus a power n as two convergent power series, such that the two series are equal to each other for all x in the open interval that contains a, because a is the center here, then they say, well, the only way this is possible is that if cn and dn were the same. And that's a uniqueness property. We've seen this uniqueness property actually in logarithms. We've seen this property in exponentials. And so the uniqueness property is kind of an extension of those ideas as well in a series, power series. Okay? Now let's look at the problem that helps us to utilize the combination of power series. Our problem reads, suppose that summation a n x power n is a power series whose interval of convergence is -1 to 1, and suppose that summation b n x power n is a power series whose interval of convergence is -2 to 2. A. Find the interval of convergence of the series summation a n x power n plus b n x power n. Okay, so this is like sum of the two series, right? So let's go to the properties related to the to combining power series. So the first property kind of works for us. It says, well, if you were trying to find the summation of cn x power n plus dn x power n, then that converges to f plus g. I'm focusing on just the plus because the problem has the plus. It converges to f plus g on I. Okay. Now our question, if you come down here, is actually asking us to find the interval of convergence. And so if you come back to the definition says it is true for I, which is the common interval. So you'll have to come back and do a quick analysis. Well, if you look at the interval for an xn, right? For an xn, now because it's xn, it must be 0, right? Centered at 0. So it's -1 and 1. This seems to be the interval for an xn. Okay. And let's call that, this is for an x power n. Okay. And the interval for bn x power n is -2 all the way to 2. Okay. Let me shade that. Okay. This whole thing is summation bn x power n. So if you look at their common interval, because the whole thing holds true only in the common interval, the common area is the black area because that's where the green and the pink overlap. And so you come back to the common area, which is between -1 and 1. Therefore, you can conclude that the interval of convergence will be -1 to 1. Okay. So I say, since -1, 1 is the common interval of convergence for summation a n xn and summation b n xn, it implies that the interval of convergence of the series, or you could just say interval of convergence, is -1 to 1 for the sum of a n xn and plus the b n xn. Okay, and that is pretty simple. We just had to look at the common interval. Here comes problem B. Find the interval of convergence of the series summation n 0 to infinity a n 3 power n x power n. Okay. Now you'll have to, this 3 power n is like an insert, right? So you'll have to go back to the general version. Okay, the general version is that summation n 0 to infinity a n x power n, right, is a series, or power series I should say, centered at 0. We know that. And for this, the radius of convergence r equals 1 for the interval -1 to 1. That makes sense, right? If you want, you could do a quick, you can quickly draw the number line here. You know, it's centered at 0. And if your interval is from -1 to 1, you know that the radius has to be 1. And that's what we're kind of combining there. This is true for all x. Okay. And if you looked at the combining power series, right, we can actually look at, okay, let me just write out what we have. We have, I want to put the 3 power, I'm sorry, not the 3, the a n 3 power n x power n. Let me write it first as it is. I want to see that if I can combine the 3 and the x, because they both carry the power n. So that will be 0 to infinity a n 3x raised to the power n, right? And so this is now your new x, right? Because that will be a n x power n, as you see here above. And if you looked at this, we said this is true for all x that lies between -1 and 1, right? If it was a n x power n. In our case, we now have in the place of x 3x. So this implies that the series converges, right, if 3x is in -1 to 1 interval. Does that make sense? So whatever is in the place of x, that's what I tried to explain in the beginning of the lecture, that whatever is in the place of x, the conditions will be translated to that x, the new x. So the interval in this problem was given to be -1 to 1, And so we keep the same interval, but the x is now not just x, but 3x. Remember, the question was to find the interval of convergence for this particular series. So then I come back and I say, okay, so if 3x must lie between -1 and 1, this is how we represent it as an inequality, right? 3x lies between -1 and 1. And this helps to solve for x by dividing each part by 3. So -1 over 3 less than x less than 1 over 3. So we always have to give our interval of convergence in terms of x, right? Because the number line simply is in terms of x. It's not in terms of 3x. So even though our problem resulted in 3x, we will use that to find the new interval and make sure that we rewrite in terms of x. This implies the interval of convergence is -1 over 3, 1 over 3. All right. So these problems utilize the combining power series properties to help us to determine the new interval of convergence. Now we talk about constructing power series from known power series. We're constructing new ones from known ones. Okay. To construct a power series from a known series, here comes the first problem. They're asking us to use the power series representation for f of x, which is 1 over 1 minus x, to construct a power series for this problem, a, which is f of x equals 3x over 1 plus x squared. Okay. So remember, the power series is the summation, right? Summation c n x power n. So we're going to build something to that form using the power series representation. So I discussed this in the beginning of this lecture, but let's do a quick check. F of x equals 1 over 1 minus x is the representation for the power series summation x power n. Okay, and remember how I mentioned about how the x has to match in all these three forms. Okay, now in our case we're given f of x, but the form is not the same as the representation. So let's rewrite this given f of x. Three x is like a constant, so I want to keep that separately. So it's like 1 over 1 plus x squared. This is the focus here. 1 over 1 plus x squared, I have to rewrite it of the form 1 over 1 minus x. You can write it as 1 minus negative x squared, right? Because your new x, as in the f of x, would be your negative x squared. Okay. So I want to just highlight that. Here I'll say this is the new x. Okay, it's like that x. Instead of that x, you now have the negative x squared. That's what we're trying to say. Okay. So if you were to represent this, okay, this would be 3x times, it's like saying f of negative x squared, right? Because now your new x is negative x squared. So using combining power series concepts and the representation, it implies that summation n 0 to infinity, I'm rewriting all this in terms of the power series up here, right? Remember, f of x can be written as summation x power n. Okay, so I'll write it like this. This implies I'll keep the 3x, okay, summation n 0 to infinity for this f of x. That's the representation as a power series. Does it make sense? So I want to bring the 3x inside the summation because that is how we denote it. So I bring the 3x here, negative x squared power n, right? So we have used f of x representation to build this series, but we need a little cleanup to do. We have arrived at the series, but notice how you have x here and there's x here. So 3x the negative, whenever you have the negative raised to the power n, we want to separate that negative 1 to the power n so that this x squared can be free of the minus, and the 2 and the n will multiply because of the product or the power rule in exponents. You multiply the powers. When powers are stacked, you multiply the powers. And then you also have this x with a power 1, so make sure that you, I'll use a different color. You know that there's a power 1 there. So you're going to combine the x's with the same base. We'll have the powers, we can add the powers. So summation n 0 to infinity 3 times negative 1 power n x power 2n plus 1. This is what we have for the as the new power series that we generated from using the power series representation function. Well, we have to give the complete information in terms of the interval, right? Because just the series won't do. We have to provide the interval for the power series. So we have to discuss a little bit about the interval. Now we know that for 1 over 1 minus x, the interval is the interval of convergence is negative 1 to 1 for all absolute value of x less than 1. Okay. Again, if you go back to here, remember this? So we have this, but this information is the same as this. Now here for our problem, we do not have the 1 over 1 minus x. Instead we have 1 over 1 minus negative x squared. So this has to also lie in this interval, but then this is going to be absolute value of negative x squared less than 1. Right? The condition now has the new x in the place of x. So let's make a quick connection there as well. You see this x here? That's the x you have to have there. You see this x here? That's the x you have to have there. Now we know absolute value returns positive, so absolute value of negative x squared is simply x squared, absolute value of x squared less than 1. And if you expand the absolute value, you get negative 1 less than x squared less than 1. And that gives us the interval, right, to be negative 1 to 1. So we got that. So the interval of convergence is the same common interval, so everything is working fine. Alright, let's go to the next part, part B. F of x equals 1 over x minus 1 times x minus 3. We still have to use the representation, which is 1 over 1 minus x. So I have to rewrite this as 1 over 1 minus x. Is that even possible? Well, it seems like we have two, not seems, it is given that we have two factors in the denominator. So is there a way to then split them up into two separate maybe fractions, and we could maybe write each fraction individually as 1 over 1 minus x format and use the combining of power series properties. So you have to think about a problem when it appears different from what we've seen before. The big challenge here is you have two factors. When you see the two factors, what comes to your mind? Especially when I say you can't keep it the way it is, you have to split it into two separate fractions maybe. Yes, you have to think about using partial fractions. I know how much you love it, but we can't help it. We have to use it, okay? So we use partial fractions to split into two fractions. If you have them as two fractions, you can think of it like this, right? You have one, I'm not putting 1, but I'm just going to change this, of course. I have x minus 1 and then plus b over x minus 3. I can very well rewrite this, isn't it? We can rewrite this as negative a over 1 minus x plus negative b over 3 minus x, isn't it? You can do all those things, and then you could, so that I have the 1 minus x format. So for the 3, I can factor out a 3, and we can do algebraically, we can get to what is desired. Because they are adding two representations, they will come out as two series, and then we can use the addition of two series. So that is our overall plan. And so for that, we need to first begin with, of course, partial fractions. So let's write this out. 1 over x minus 1 times x minus 3, according to partial fractions, says we can split it as a over x minus 1 plus b over x minus 3. This is because they are distinct factors, right? If they were repeated factors, then we have a different format. Okay? Distinct factors. And we're going to set the coefficients equal to each other. So 1 equals a times the x minus 3 plus b times the x minus 1. So collect all the terms that have the x in it. So a plus b times x. And collect the terms with a constant. So negative 3a minus b. Yeah. So we have the x terms and the constant terms separated so that we could set them equal to the corresponding coefficients on the other side. On the left hand side, there is no x term, right? There is no x term implies that 0 equals a plus b for the x. I'll just write that up here for x. For constants, 1 is on the left hand side and negative 3a, negative b is on the right hand side. Okay, so you'll have to solve them simultaneously. I'll come to the left side first, and I want to write a as negative b, right? That's what it implies. So a equals negative b. I want to use that on the right hand side now. Okay, so 1 minus negative 3a. Okay, and negative b is a, isn't it? So I want to do plus a. Negative b itself is a. So 1 equals negative 2a, which implies a equals negative half. If a equals negative half, I come back here and then say, okay, a is negative half equals negative b, which implies b is positive half, right? Negative. So divide both sides by negative, you get negative, I mean the negatives cancel off, giving you a half. So we've got a as negative half and b as half. So let's come back here to our given problem. 1 over x minus 1 times x minus 3 is now negative half over x minus 1 plus positive half over x minus 3. Make sure you put them under the right factors. Okay. All right, now let's see. That'll be a negative 1 over 2 times 1 over x minus 1. I want to keep the 1 over x minus 1 separate from the other constants. Okay. Remember, I want to rewrite this x minus 1 as 1 minus x. So I really need room for all that, to make all those changes. Okay. So 1 over x minus 3. Now the order is switched, right? I want 1 minus x and I want the same style here. So if the order is switched, I have to factor out a minus. So we'll come to that. I need a little more room, so I'm going to move a little to the left. So I have the negative half, and I factor out a negative 1 so that in the bottom the order reverses. Okay, and then plus here I have the half, and then here also I factor out a negative 1 so that the order reverses in the bottom. That's what happens when you factor out a negative, right? Okay, so that makes the first term positive, so 1 over 2 times 1 over 1 minus x. This is looking good, so no changes there. 1 over 3 minus x. Now we have a problem. We want a 1 minus x, not a 3 minus x. How do we handle that? Simple. You divide up and down by 3, and that will take care of that dilemma. So I'll just say divide up and down by 3. These are algebraic manipulations, so you can do these things as long as you maintain or preserve the balance of your fraction. So that will be 1 over 3 over 3 over 3 minus x over 3, isn't it? So I want to kind of change this 3 over 3 to a 1. Now this 1 over 3 on the top could be brought down and made into, combined with this constant half, so that we have a 1 over 1 minus x. Now in the place of x, we now have x minus 3 for the second term. So I'm going to do that cleanup here in the next step. Minus 1 over 2, and the 3 will combine to give us a 6, times 1 over 1 minus x over 3. Okay? So now I have two separate terms, so I'll have two series coming out of this. Okay? Now we already know that this one is summation n 0 to infinity x power n, right? And what do you think about this? This one will be summation n 0 to infinity. Instead of x, I now have x over 3, so it's going to be x over 3 power n. Right? Now remember that these have their own intervals or conditions, right? When I say intervals, I mean they're still in the same interval, -1 to 1, but then we have to look at the intervals in terms of the new x. So for this, it will be for all x between -1 and 1, right? Remember, absolute value of x less than 1, that expands as this. And for this, it will still be between -1 and 1, but now your new x is this x minus 3. Right? So keeping that in mind, we will now, kind of combine these two. So half times summation n 0 to infinity x power n minus 1/6 times summation n 0 to infinity x over 3 power n. But remember, we want the constants to be pulled inside. So it's summation n 0 to infinity half x power n minus summation n 0 to infinity 1/6 x over 3 power n. Yeah. Now, because they go to the same interval, right, we can combine these two. Remember, on the left-hand side, we had 1 over x minus 1 times x minus 3. Right? That was on the left side. So now I'm combining the series, because that's allowed by combination. Combining power series property allows us to, because they have the same interval, right? They go on the same interval, -1 to 1. We have (1 over 2 x power n minus 1 over 6 x over 3 power n). Yeah. So technically we are done here. I do want to quickly come back and give you a quick. Remember, all this is true. You can combine this for the common interval -1 to 1. If you can't find a common interval, we are in trouble. Okay. So for that, I want to quickly draw your attention to the information we have laid out here. This is good. Right? This one, if you expand it, if you multiply by 3 everywhere, right? This goes away. This gives us -3 less than x less than 3. So look at the intervals changing. So this goes back to what we saw earlier. This is -1 to 1. So your interval would be in between these for this first one. Right? For the second one, it goes from -3 to 3. And that interval will be this whole thing. And notice how you have the black region, which is the common region between -1 and 1. So that is why we're able to use the combining power series property, because even though they go to, it appears that they go to different intervals, their overlapping intervals is the common region, and so this can be combined for the common region, -1 to 1. You can't expand it for -3 to 3. It's good for the common region, -1 to 1. Okay, now that we are done with this, we now have to go back and clean up. You have the x power n and the x power n, so we want to separate the constants from the x power n. Three power n, right? I'm expanding the x over 3 power n as x power n and 3 power n for all x in the interval -1 to 1. And then summation n, 0 to infinity, 1 over 2 minus 1 over 6, 3 power n. It looks like 63 power n, so let me do 6 times 3 power n with an x power n. Okay. So this whole thing is like your Cn. Or if you looked at our combining properties, right? In those properties we had this whole thing could be written as b x power m Cn and so on. So it could be any one of these forms. Now we do not have any x term here, right? In this constant part. If you had any x term, then it would appear as this, b x power m and then Cn. But because we didn't have any x term, this would be your Cn itself, right? So you're able to see that it is coming back in the format we want. So we were able to find a new or generate a new power series from power representation. Okay. So that's this problem where, in fact, two problems that we did. So let me reiterate this information here. Look at this. You were given a function and you were asked to generate a power series, right? And for that we use the power series representation of this function, f of x equals 1 over 1 minus x. So this was basically our big deal that helped us to develop or create these new power series. Now we're going to do the other way around. Okay, we will be given power series and we need to find the function that represents it. Just like how f of x equals 1 over 1 minus x represents the actual series, we're going to go the other way around. Okay, we'll be given the series and we have to find the corresponding function. So let's get to that. Finding the function represented by a given power series. Consider the power series, summation 2 power n x power n, and find the function that represents this series and determine the interval of convergence. Okay, let's begin with the series itself and see where it leads us. Summation 2 power n x power n. In fact, you could write this as summation 2x raised to the power n, right? Now remember, this is kind of representing this in turn was equal to 1 over 1 minus x, which was our f of x. Remember? We're doing the reverse, so I'm starting with the series. Previously we started with the function and went to the series. Now we're starting with the series and going to the function. Therefore, in the place of x, I now have 2x. So I can rewrite this series as the function 1 minus x, but in the place of x I have 2x, right? 1 minus 2x. And this is true, this will be your f of 2x, right? For all absolute value of 2x less than 1. Okay. You can write it as an absolute value representation because it's more like a nutshell, or you could expand it like this. We are going to expand it because we need to find the interval of convergence. So this implies your interval of convergence would be first to expand this absolute value. So 2x will lie between -1 and 1. Then go one more step and divide by 2 in each part. So your interval of convergence comes out to be -half less than x less than half. Yeah? So the new function f of x. We call it f of x because that's a general format. So you don't say 2x because you're trying to create a new function. So the new function f of x is 1 over 1 minus 2x for the given power series summation n 0 to infinity 2 power n x power n, and we found the interval of convergence to be negative half comma half. So that was neat. Now we will, and then you could look at other examples furthermore if you wanted in the book. This is the general idea. So you're trying to see what ways you can represent it as 1 over 1 minus x format. Okay. Now we'll move to multiplying power series, and this would give us a special kind of product known as the Cauchy product. So we'll talk about that now. Multiplying power series. Suppose you have two power series, Cn xn and Dn xn, and they converge to f and g respectively on a common interval I. Then En, we would define En to be a combination of the C and the D, right? So En is C naught Dn plus C1 Dn minus 1 plus C2 Dn minus 2 and so on, and it ends with Cn D naught. If you were to simplify, combine this and write it as a generalized notation, the series would be summation k 0 to infinity ck dn minus k. Okay, we use k here because we are only trying to define En. Okay, and En has the n in it, but it's generated from k going from 0 to infinity. And then we say, if that's the case, then summation n 0 to infinity Cn xn times summation n 0 to infinity Dn xn will be equal to summation n 0 to infinity En xn. Okay, that's why we defined En before. So you have En xn, which is a combination of the Cn and the Dn and the xn. Okay, and we're saying that this En xn, the series, will converge to f times g because Cn is represented by f and Dn is represented by g. It converges to the product of f and g on that I. And the series summation n 0 to infinity En xn is known as the Cauchy product of the series Cn xn and Dn xn. Okay, so it looks a little complicated. The product of Cn and Dn, right? Cn xn and Dn xn, x power n. That product gives you a new result, which is En x power n, and we defined what En stands for. This special series is known as the Cauchy product of the two series. So we'll do a problem here. Multiply the power series. I should say power series representation. So we have 1 over 1 minus x, which is summation x power n. We've seen this so many times now. But this is the problem, so we're expanding it for us. Okay. You want to multiply this with 1 over 1 minus x squared for all x, absolute value of x less than 1. Okay. They have the same, they have common interval, and then they have the functions that they go to. We want to use these two to construct a power series for this new function, which is a product of these two. On this same interval negative 1 to 1, right? Absolute value of x less than 1 is the same as going from negative 1 to 1. Okay, this is our problem. We have the power series representation, and we're asked to construct a new power series for the product of these two. All right, so let's begin with multiplying the two series. One plus x, this one, right? The series, the expanded version. So 1 plus x squared plus x cubed, and so on. I'm multiplying this series with the other one, which is 1 plus x squared plus x power 4, and so on. Okay. It's going to be tedious, of course, but let's begin to, let's at least attempt to distribute for the first few terms. Okay. So because it's going to be, a mega expansion, I want to go over this first, and then we will write out the expansion. This whole thing is to be distributed to each term here, right? That's what happens. And then within that, you will have, because each term itself has a collection, each distribution has a collection of terms. And so when you did this whole thing times the 1, that expands as 1 plus x squared plus x cubed, and so on. Then when you multiply this with the second arch here, right, with the x squared, then you can think of that x squared multiplying here as x squared plus x cubed plus x power 4 plus x power 5, and so on. Then the third arch would be this x power 4 that is being multiplied to this whole thing. So that's going to give us x power 4 plus x power 5 plus x power 6 plus x power 7, and so on. Okay? So that is our understanding. So that's what I want to... It's going to be tedious if I wrote them all out. Okay. Nevertheless, we'll give it a shot. Okay. Okay, we have that's the first arch plus that's the second arch. The third one would be x power 4. It starts with x power 4 plus x power 5. And if you were to expand this to the next one, it will be x power 6 here, right? So it will be x power 6 plus x power 7. Right? You begin to see that. Now what we see is that you can group it in so many ways. One of the ways we can group this is to group it as what we see is that your x squared, x cubed, they repeat, isn't it? Right? The x squared and the x cubed here repeats here. Then the x power 4, x power 5, that repeats here. So you can see a pattern there. Okay. Or what if you multiplied it the other way around? Okay, that's the other, just to see for patterns. So I'm encouraging you to be open about the possibility you'll get when you expanded it by rearranging the orders, because with multiplication that is possible, right? This time I'll use and try this and see if you get a better pattern. If you do, good for us. Okay. So that's going to be 1 plus x squared plus x power 4, etc. plus x times, that's the second arch, right? So if you want, I can put 1 times here. So x times 1 plus, I'm not expanding it fully like before. The advantage of using this method, okay, is that you have the 1 times the series plus x times the series. That this part is the same, right, throughout, and you have the 1 plus x squared format. Okay, so this kind of helps you to separate all the, so it doesn't matter whichever one you chose, it just helps you to separate all the even terms, even powers and all the odd powers, and see how many times they repeat, right? So it doesn't matter whichever method you use, but I want you to be open to the idea that you might find a nice pattern if you were open about the order in which they separated. Alright, so what I'm trying to do here now is to separate all the even powers. So I'll keep the one with the even powers, right? 1 plus x squared plus x power 4. For that, I'll have to expand this a little bit. Okay. No matter which method technique I chose, this is how it expands, right? That was the next one. With the second representation, the second distribution style, what is nice is that it does automatically separate out as even and odd powers. Right? I just like to see it that way, just so I can account for how many repetitions there will be. Okay, so if I were to do this for the x power 4 times the expression, that x power 4 would begin with x power 4 plus x power 6 and so on, isn't it? And x power 5 would start with x power 5 plus x power 7. So if you can see the pattern, I can see that the x squared repeats twice. Okay, x power 4 also repeats twice. If I go for, not twice actually, 3 times. Let's remove that. 3 times. Because if I expanded in the next step, I will not find the x power 4 because we would have exhausted that. The next term would be x power 7, right? I would say x power 6. Okay. And likewise, if you look at the x cubed, I have 2x cubed there. And I have 3x power 5 there. And what do you know about x power 6? Okay, I could because in the next step, I would have had, starting from x power 6, x power 8, and so on, right? If I were to expand this pattern, and this would be x power 7 plus x power 8. I'm sorry, not 8, x power 9. So it's all odd there. And this helps me to see that if it was x power 6, I would have had 4 such x power 6. There would have been 1 on the top here. And there would be another x power 7 here. So I'd have 4 of them. You're beginning to see that pattern. Okay. Now, it's a little drawn out for us, but I wanted to show you how the pattern can be arrived if we were able to see that. Now it's easy for us to kind of combine them. So I'll say there was only one of 1, and there were 2 x squareds. And this side there were 2x cubed here. Then we have 3x power 4 plus 3x power 5 plus 4x power 6 plus 4x power 7 and so on. So what we see is now we've built a series here, right? That was the question. They wanted us to build a series, and we found a series that comes up. In fact, I just noticed I missed the x. Let me fix that quickly. There was a 1 plus x plus 2x squared. Alright, and then we'll just conclude and say, since the series for y equals 1 over 1 minus x and y equals 1 over 1 minus x squared both converge on negative 1 to 1, the series of the product, right, the one that we just built above, also converges on negative 1 to 1. Okay, and that was to do with constructing a power series for the product. Next, we look at term-by-term differentiation and integration for power series. Okay, remember we're putting this in the function format. So once you have it in the f of x format, we can use the ideas of differentiation and integration freely, because it's provided the function is integrable and differentiable. Okay, as the name goes, it's term-by-term differentiation and integration for power series. So we say, suppose the power series is centered at a and converges on the interval a minus r, comma a plus r for some positive r. Then the function is defined as, the f of x itself is summation cn x minus a power n. And you would expand it like this, right? We're saying f is differentiable on this interval a minus r to a plus r, and we can find that f prime, it's differentiable, right? So f prime can be figured out by finding the derivative for individual term by term. So you can see this written down here as f prime of x is summation, let me take you here. So this, if you were to differentiate, would be, of course, summation, cn n times x minus a power n minus 1, right? That's what we have here. We just have the n thrown in the front before the cn. So that's the same information here. Okay? And that is expanded here for us. If you can't see it together like that, you can differentiate them term by term. That's what this says. We are trying to give it to you in a collective manner here, but you can definitely do it step by first expanding f of x and take the derivative for each one of them. This will be 0, c1 plus c2 times 2 times x minus a, and so on, right? So that's what you have here as expanded in the expanded form. Remember, this time the interval is not negative 1 to 1 as we saw previously, but it's based on the r, the radius of convergence. We can also integrate this, right? And when you integrate it, let me take you back here. This was for derivative, right? Let me erase that. When you took the integration again, summation cn is the constant, x minus a power n plus 1 over n plus 1, right? That's what you do, because that is where the n, that is where your x is, because it's f of x. So the terms with the n doesn't matter, the terms with x matters, and so you're only worried about that. Okay. The one other thing we see in the integration is that you always have, because it's an indefinite integral, you have that plus c, right? When you take the derivative, that c is what is thrown in the front. Okay. All right, and when you expand this, you get this. So we're saying, because it's series, you can expand it, and because you can expand it, you can definitely take the derivative or the integral term by term. Okay, time to do a problem. Use f of x equals 1 over 1 minus x to represent g of x, which is 1 over 1 minus x squared on negative 1 to 1. Okay. Again, we're playing with the same stuff we've seen before, right? But this is a little more interesting because there is a connection you can see between f and g. Okay? If you look closely, g is actually the derivative of f, isn't it? Okay. So then let's make a quick note and say, since g is a derivative of x, derivative of f of x, we can find a power series for g by differentiating f term by term. Isn't it? Now we know that f of x has a power series, right, which is summation x power n. We don't have such a power series for g. So we can find that power series for g using the fact that f is a derivative, right, So if you took the derivative of f, you get g, because g is a derivative of f. So if you take the f prime term by term, you get g, and that is our focus here. So we'll start with what we have. G of x is 1 over 1 minus, oh gosh, I apologize, I copied the question wrong. It should be 1 minus x squared. Only then will it be a derivative. So you might have been wondering, how can it be a derivative? Now it will be. Sorry about that. Okay, so it's 1 minus x the whole squared, not just the x squared. Okay, that makes sense. To kind of help us see that, okay, 1 over 1 minus x can be written as 1 minus x power negative 1, right? If you took the derivative of this, you get negative 1 times 1 minus x power negative 2 times negative 1. Remember chain rule? So the negative and the negative becomes positive. So you just get 1 minus x power negative 2, which becomes 1 over 1 minus x power 2, positive 2, which is g of x. So we started with f of x, and the derivative, f prime of x, is g of x. Okay? So I'm going to call upon that information here and say, well, this is derivative of 1 over 1 minus x. Right? That's a derivative of f. And because we already know the power series for f to be summation x power n, n0 to infinity, if we derive this term by term, we should be good. So let's expand this. So 0 would be x power 0 would be 1 plus x squared. Now take the derivative term by term. So that becomes 0. Derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. Next would have been x cubed, right? So that will be 3x squared, and so on. So if you want to generalize this, this is your series, but if you wanted to generalize this and write it as in the series notation, you can write it as n plus 1 times x power n for all absolute value of x less than 1. So we were able to find a series for g by seeing the connection between g and f and using derivative of term by term differentiation to produce a new power series for g. The next question depends on this one. So it says, use the above result to evaluate the sum of the series n plus 1 over 4 power n. To help us kind of put things in perspective, remember the left-hand side for the Brown working is g of x, and g of x in turn is 1 over 1 minus x the whole squared. Because we have to use the above result, I want to make this connection very clear. 1 over 1 minus x squared on the function side gives us the, oops, this one got lost, gives us the power series n plus 1 times x power n. Okay. All right, let's begin with summation n plus 1 x power n. Okay, what we have above, we know that that is 1 over 1 minus x, the whole thing squared. Okay. Now if you look at our problem, we have that n plus 1 matching in the green, right? In the place of x, I have the 4 power n in the denominator. So in our given problem, I see this x as 1 over 4, right? And that's what I'm trying to make. That's a connection I'm trying to make. So then, if I had summation n 0 to infinity n plus 1 times 1 over 4 power n, right? This 1 over 4 power n can be written as 1 over 4 the whole thing power n, so that it matches with the x. And you know that whatever is in the place of x, that has to be matched here. So in the place of x, I now have 1 over 4. And that has to be squared. So let's make that connection. That has to go there. Okay. And now it's literally arithmetic. 1 minus 1/4 is 3/4, and you're squaring that and then flip it. That gives us 16/9. And then let's wind up with one integration problem. Integrate f of x equals natural log of 1 plus x. Okay. Don't be stunned by this problem. See if you can utilize integration to come up with a power series, right? Our job is to find the power series for this particular function. Okay. Because this is differentiable, first find f prime. We're trying to integrate it, so no problem there. We were going to use actually fundamental theorem of calculus, right? Because you know that integration and the derivative will undo each other, giving us the function. So I'll call upon that in the end. So that's the reason I'm first doing the derivative. So it's ln, right? So it's going to be, do the u substitution. Oops, I'm sorry. We are doing the derivative. Why did I do the u substitution? Well, what I meant in the background was chain rule. Remember the chain rule. Not, they are interconnected. And so sometimes I tend to use that approach, but I meant the chain rule. Okay. In this case, it's fine because you get times 1, so we're fine. All right, so derivative of natural log of 1 plus x is 1 over 1 plus x. Okay. And remember, we want to write this as 1 minus a negative x so that we could use the 1 over 1 minus x format. So our new x is negative x. Okay. So if you were to put this in the series notation, remember the 1 over 1 minus x was x power n, right? But now it's not the regular x. We now have the x, the new x to be negative x. So I put negative x power n. Expand this. 1 minus x. Because of the negative, there will be alternating signs. And so on. And on the left side, we have f prime of x. Right? Now we use the fundamental theorem of calculus and take the integral. Integral of this dx would allow us to take the integration individually, right? So that will be 1 minus x plus x squared minus x. So if I were to apply the integral on both sides, you can see that. Now we will take the integration term by term. Integral of 1 dx, integral of dx, right? That will be x minus integral of x dx will be x squared over 2 plus integral of x squared dx will be x cubed over 3. Am I getting the signs right? Yeah. Oops. And then we have, oh, and then the plus c, because it's an indefinite integral. So we throw the c in the front. And then if you want to generalize this and give a series notation, then you can go from, let's see, the first one is some constant, right? x power n over n, because that's what you're getting everywhere, right? And then the negative 1 because of the fluctuating series. And with the n as 0, right? If n is 0, so this will be we have the first term to be constant. For the second term, when you want to get an x, you want the x to have the power 1, right? So when n is the power 1, then it becomes 1 x power 1 over 1, and here this will be 1 plus 1, 2. So because it's the positive, even power, negative 1 power 2 would give back a positive sign. So you know that that's how it starts, right? And so you want to incorporate that. Okay. And let's see. So we did we always have to check when we do the generalization and write up a power series. So this section was helpful in helping us figure out some important stuff. For instance, we learned about going from, well, we did see the combining power series and uniqueness properties, but what was really cool was we learned how to use a given function to construct a power series, and vice versa. We were given a power series and we used that to construct a function. In both cases, we mostly relied on this 1 minus, let me write that here, 1 over 1 minus x condition, right, which was summation x power n. So we used that relation mostly to build on these things. We also got an introduction into the Cauchy product. We didn't do much problems there, but we were able to look at one problem that used the multiplication of power series. And then we finished off with term-by-term differentiation and integration for power series, all because of the ability to bring in the F notation for these series. All right, class, I hope you enjoyed this. I will see you in the next video.